As 2017 comes to a close, it does so in the realm of exoplanet research, having answered two very important questions that previous years had raised. At the beginning of the year, our solar system appeared unique in terms of the sheer number of planets present, the number of planets orbiting within the habitable zone of a single star, and the fact that our four terrestrial planets are segregated in closer orbits to the Sun than those of the four gas and ice giants. We now end 2017 knowing that our solar system is not unique in any of those categories. The list of known exoplanets exists almost exclusively in a small section of the Milky Way that's visible from Earth in near-Earth space. Beyond that, a few possible extragalactic planet detections are currently under evaluation for confirmation. Also pending confirmation are more than 5,000 exoplanet candidates identified to date via NASA's Kepler Space Telescope. To date, the total exoplanet count stands at 3,710 planets scattered across 2,780 star systems, with 621 of those stellar systems containing more than one planet. 1-5 Sun-like stars known to contain at least one Earth-sized planet orbiting within the star's habitable zone, and knowing there are approximately 200 billion stars in the Milky Way alone, there are hypothesized to be 11 billion habitable, Earth-sized planets in or around just Sun-like stars, a number that jumps to 40 billion habitable Earth-sized planets in the Milky Way when red dwarf stars are included. This figure shows the number of systems with 1, 2, 3 planets, etc. Each dot represents one known planetary system. We know of more than 2,001 planet systems, and progressively fewer systems with many planets. Credit NASA Ames Research Center Wendy Stenzel and the University of Texas at Austin Andrew Vanderberg, and red dwarfs are where the vast majority of the exoplanet discoveries have thus far occurred because red dwarfs are small and their planets orbit in very quick periods of days or a few weeks, meaning optical telescopes can observe multiple transits of those planets across their stars' disks in short periods of time. Of all the exoplanets discovered around red dwarfs to date, 2017 provided the biggest shock and perhaps most important of all those discoveries. An ultracool red dwarf, slightly larger than Jupiter but much more massive, lies 39.6 light-years from Earth and hosts not one, not two, but 7 Earth-sized terrestrial planets. The groundbreaking discovery came from a team using the Transients Planets and Planetesimals small telescope TRAPPIST in Chile, who in 2016 identified 3 possible planets in the TRAPPIST-1 system. Follow-up investigations by ground-based telescopes, including the European Southern Observatory's Very Large Telescope, and NASA's Spitzer Space Telescope, confirmed 2 of the 3 exoplanets. But Spitzer ended up seeing more than anyone expected, 5 more exoplanets. All rocky, all Earth-sized, all capable of having water on their surfaces under the right atmospheric conditions. And 3 of those 7 exoplanets were found to orbit within the habitable zone of the TRAPPIST-1 star. The discovery shattered previous records for number of terrestrial exoplanets found orbiting the same star, number of terrestrial planets in any known stellar system including our own, and the greatest number of planets orbiting within the habitable zone of a single star outside our solar system. This artist's concept shows what each of the TRAPPIST-1 planets may look like, based on available data about their sizes, masses and orbital distances. Credits NASA Caltech note TRAPPIST-1 might actually represent the greatest number of planets known to orbit within the habitable zone of any star, including our own. Depending on which scientific study is used, Venus is sometimes including as having its orbit lie just within the Sun's habitable zone, while other studies show Venus to definitively exist outside the zone or barely graze the innermost edge of habitable zone at its aphelion. In almost all accepted studies, both Earth and Mars lie firmly within the Sun's habitable zone. Initial observations and measurements of the TRAPPIST-1 system from Spitzer allowed scientists to precisely measure the sizes of the 7 planets and develop mass estimates of 6 of them, thus allowing their densities to be estimated. But much was still uncertain about the planets' orbits and their orbital relations to each other. A few months after the initial discovery was announced, additional observations and study of the system by the TRAPPIST telescope, Spitzer telescope, the Hubble Space Telescope, the Kepler Space Telescope, and other ground-based telescopes were compiled, revealing a regular pattern in the orbits of the planets that confirmed suspected details about the orbit of the outermost and least understood planet TRAPPIST-1H. The data showed TRAPPIST-1H was located 6 million miles from its dwarf star and had an orbital period of 19 days. Determining TRAPPIST-1H's predicted orbital period and location was accomplished by looking at the other 6 planets of the system, whose orbits and locations were known. In so doing, scientists quickly identified a mathematical pattern in the frequency at which each of the 6 innermost planets orbits their star. This complex but predictable pattern, called an orbital resonance, occurs when planets exert a regular, periodic gravitational tug on each other as they orbit their star. What the data showed was that the planets were all in a stable resonance with some of their counterparts. When the 3 farthest planets TRAPPIST-1F, 1 Gram, and 1H were considered separately from the 4 innermost planets, scientists found resonance markers in TRAPPIST-1F and 1 Gram that indicated a stable 3-way resonance with TRAPPIST-1H. The team then extrapolated from the observed resonance between 1F and 1 Gram and used that to predict where TRAPPIST-1H's orbit was, what its orbital period was, and where in its orbit it should be to match the stable resonance it was believed to have with its counterparts. And the collected telescopic data revealed TRAPPIST-1H exactly where the orbital resonance predicted it to be. Artists' impression of TRAPPIST-1H in orbit of its red dwarf star. Credit NASA, it really pleased me that TRAPPIST-1H was exactly where our team predicted it to be. It had me worried for a while that we were seeing what we wanted to see. After all, things are almost never exactly what you expect them to be in this field, said Rodrigo Luga, doctoral student at UW in Seattle, and lead author of the compiled study. Nature usually surprises us at every turn, but, in this case, theory and observation matched perfectly. Moreover, the TRAPPIST system discovery could be a significant piece in the puzzle of finding habitable environments, places that are conducive to life, said Thomas Zurbuchen, Associate Administrator for NASA's Science Mission Directorate. Answering the question, "Are we alone?" is a top science priority, and finding so many planets like these for the first time in the habitable zone is a remarkable step forward toward that goal. A key element for understanding whether life on known exoplanets is possible is understanding the age of the star those planets orbit. Young stars are prone to tantrums, releases of high-energy radiation called flares that can zap their planet's surfaces. If the planets are newly formed, their orbits may also be unstable. On the other hand, planets orbiting older stars have survived the spate of youthful flares and have also been exposed to the ravages of stellar radiation for a longer period of time. This illustration shows what the TRAPPIST-1 system might look like from a vantage point near planet TRAPPIST-1F at right. Credits NASA Caltech. At the time of its discovery, scientists believed the TRAPPIST-1 system to be at least 500 million years old, since it takes stars of TRAPPIST-1, their slow mass roughly 8% that of the Sun roughly that long to contract to their minimum size, just a bit larger than the planet Jupiter. As it turns out, those initial estimates were wrong. Really wrong. TRAPPIST-1 is old. Really old. According to new information released in August, researchers now believe the TRAPPIST-1 systems to be 5.4 and 9.8 billion years old, up to twice as old as our own solar system, which formed about 4.5 billion years ago. Our results really help constrain the evolution of the TRAPPIST-1 system because the system has to have persisted for billions of years. This means the planets had to evolve together, otherwise the system would have fallen apart long ago, said Adam Bergasser, an astronomer at the University of California, San Diego, and the study's first author. Understanding the age of TRAPPIST-1 raised questions about its septuplet of planets and their ability to host life as we understand it. Since the planets are so close to their star, they have soaked up billions of years of high-energy radiation, which could have boiled off atmospheres and large amounts of water, making their habitability less likely than first thought. Artists' rendering of a solar storm hitting Mars and stripping ions from the planet's upper atmosphere. Credit NASA. If this is the case, the equivalent of an Earth ocean may have evaporated from each TRAPPIST-1 planet except for the 2 most distant planets G and H, just as Mars lost most of its water and atmosphere to the Sun's high-energy radiation over billions of years. However, stellar and planetary old age do not necessarily mean that a planet's atmosphere has been eroded. Given that the TRAPPIST-1 planets have lower densities than Earth, it's possible that large reservoirs of volatile molecules such as water could produce thick atmospheres that would shield the planetary surfaces from harmful radiation. A thick atmosphere could also help redistribute heat to the dark sides of these tidally locked planets, increasing habitable real estate. But this same feature could backfire in a runaway greenhouse process like Venus, where the atmosphere becomes so thick that a planet's surface overheats. Nonetheless, the long lifespan of small stars like TRAPPIST-1, which range into the trillions of years, longer than the Sun's comparatively short lifespan of just 10 billion years, means the system is still relatively young, and the star has a temperature and brightness that remain relatively constant over trillions of years. Another look at the 7 Earth-sized planets next door. At NASA Kepler dataset on the TRAPPIST-1 system available now. https://wcgc1uf8pic.twitter.com/1leo6v3 NASA Day PL at NASAJPL March 8, 2017. Stars much more massive than the Sun consume their fuel quickly, brightening over millions of years and exploding as supernovae, said Eric Mamajek, Deputy Program Scientist for NASA's Exoplanet Exploration Program. But TRAPPIST-1 is like a slow-burning candle that will shine for about 900 times longer than the current age of the universe. All of which sets up the potential for life to have taken a life that might take a very different evolutionary journey than it has on Earth. Regardless, TRAPPIST-1, while fascinating, wasn't the only extrasolar system this year to prove that our solar system is not unique. Until just this month, our home stood alone and at the top of the list of planetary systems with the most number of planets, 8. When TRAPPIST-1's 7 planets were confirmed, it joined HD 10180 and Kepler 90 as the only 3 systems to come closest to us with 7 confirmed planets each. But that all changed on the 14th of December 2017 with the announcement of a new addition to the Kepler 90 system. With Kepler 90, our solar system was no longer alone. There was a confirmed second stellar system with 8 known planets. What's more, the Kepler 90 planets do not orbit a red dwarf. They orbit a main sequence G-type star, just like the Sun. The Kepler 90 system is located 2,545 light-years from Earth in the constellation Draco, and the discovery of the 8th confirmed planet Kepler 90I was found to be a super-Earth with a radius of 1.32 that of Earth and be in an orbit positioned 0.1234 astronomical units from its star, giving the planet an orbital period of 14.449 days. Its position places it as the 3rd planet in the system. In comparison to our solar system, Kepler 90I orbits 5 times closer to its Sun-like star than Mercury orbits to the Sun. While the number of known planets in the Kepler 90 system now matches that of the known planets in our own solar system, Kepler 90 is extremely compact, with all 8 of its planets orbiting their Sun-like star inside the orbital distance of Earth. In fact, the 4 closest planets to Kepler 90, Kepler 90b, C, I, and D all orbit closer to their star than Mercury does to our own. Kepler 90e orbits at roughly the same distance as Mercury, Kepler 90f orbits roughly halfway between the orbits of Mercury and Venus, Kepler 90 grams orbits just inside the orbital distance of Venus, and Kepler 90h, the farthest known planet in that system, orbits just inside that of Earth's. Moreover, the total number of planets in the Kepler 90 system isn't the only thing about that system that proves our solar system is not unique in composition. In our solar system, all of the known terrestrial rocky planets are grouped together in the inner solar system while all of the known gas and ice giants are grouped together in the outer solar system. No extrasolar system discovered prior to Kepler 90 matches this type of grouping, with all of the rocky planets orbiting closer to the star than the gas giants. Kepler 90 is a Sun-like star, but all of its 8 planets are scrunched into the equivalent distance of Earth to the Sun. Credit NASA Ames Research Center Wendy Stenzel. Yet the Kepler 90 system, with all of its 8 identified planets, is a match to this configuration, with the 3 innermost planets being terrestrial while the 5 outermost planets are gaseous. Moreover, as with our solar system where the gas giants are believed to in some way help protect the inner terrestrial planets from asteroid bombardment due to their sheer gravitational size and influence, the outer 2 gas giants of the Kepler 90 system are also believed to serve a similar protection role, though not from asteroids but in terms of the Kepler 90 system's survival. Kepler-90's 8 known planets are all close to being in orbital resonance with other planets. The period ratios B, C, and D are close to 45, 35 and 14, respectively. Planets D, E, F, G and H are close to a 234,711 period ratio. Meanwhile, F, G and H are close to a 358 ratio. These near-orbital resonances are believed to be caused by the outer two gas giants, which facilitate the formation of closely packed resonances among the inner super-Earths. What's more, our telescopes have only probed the innermost portion of the space surrounding the Kepler-90 star, meaning a vast area surrounding this sun-sized star has yet to be explored for the possibility of other planets caught in its gravity, making Kepler-90 an excellent candidate for the first system known to contain more than 8 planets.